Alright, so let's start with a velocity time graph, which is a generic graph, where meters per second is our unit for velocity and time is in seconds on the horizontal axis. Let's let this initial velocity be v naught. The little sub-zero is a symbol that we call naught, N-A-U-G-H-T, which means nothing or the beginning, and it's used very commonly in physics. So I have v naught here at the beginning, and then our ending velocity for this little segment we'll just label as v. We usually just use a plain symbol to represent the final. And that occurs at a time, and I'm going to make it a generic t for the time, and the beginning time is 0. So first of all, the slope of this velocity time graph gives us acceleration. We should have discovered that in our constant acceleration activity, that the velocity was changing, which resulted in a acceleration. Okay, so the acceleration would be the change in velocity over change in time, and our change in velocity would be v minus v naught, and our change in time is t minus t naught. In our case that's 0, but t minus t naught. Okay, so we can come up with the acceleration there pretty easily. Now one thing we should be able to do is write the equation for that line in terms of generic y equals mx plus b. So this is v is equal to at. That's the equation for that line. Plus, now remember, b is the y-intercept, so that should be our v initial, v naught, circled in red on the graph. So v is equal to at plus v naught, but you usually don't see it written that way. Usually you see it written as v equals v naught plus at. That is your first kinematics equation. Most of the time you guys like a box, so there's your box. And each one of these variables defined, final velocity, initial velocity, acceleration, and time, and they all should be in SI units. Kilograms, meters, seconds. Those are all SI units. And we can also find the change in position of the object from the beginning time to the end time. So go back up here and let's look at our graph. We've got meters per second and seconds. Now, I've found the slope of that line, and that gave me meters per second, or meters per second squared. What if we were to find the area under that graph? So let's segment it into pieces. So from the blue line all the way down to the time axis, that area would be the change in velocity, change in position, change in position, delta x, for the object. Now, you could use whatever the equation is for that strange shape, or you can just split it into a rectangle and a triangle, which is what I'm going to use because I don't remember the fancy equation for that shape and I don't really have to. So let's do this dark pink solid area, and then we'll do the triangle area. All right, so let's write down what we've got. Our change, or our area, is base times height, so that would be t times v. And that gives us seconds times meters per second, which gives us meters. Yay! That's the correct unit for change in position. So that's all good. Change in position is also known as displacement. Remember, displacement is different than distance. All right, so we can do these two different shapes, the rectangle and the triangle, to find our displacement. All right, so I had to copy it down here. Okay, so let's see. Our delta x is equal to, we'll do that rectangle first, base times height, or height times base. And our base is t, but our height is v naught. And it doesn't matter which one comes first, but if you look it up in a textbook, you'll see the v initial written first. Now we need to add the rectangle. We add the rectangle, one half base times height, but height in this case is that little height right there of the triangle, and that's v minus v naught. So 1/2 the base times t times the height v minus v naught. Now, that's kind of ugly, but if a is equal to v minus v naught over t minus t naught, and t naught is 0, then we can rewrite v minus v naught or at as v minus v naught, and make a substitution. So then we'll get a delta x equals v naught t plus 1/2 t times at. And t times at is at squared. So this is our second kinematics equation. Now notice, these are not falling out of the sky onto your page. These are not some equations that you've just read in a book. These equations, these two formulas as you might like to call them, come from using our graphs. Graphs are so very powerful. So delta x is your displacement, v naught is initial velocity, a is acceleration, t is time, and in SI units we'd have meters, meters per second squared, and times in seconds. So this equation comes from a generic under the graph, finding the area under the graph. And that's really important because now instead of graphing every problem to find the change in position or to find the final velocity, you can use these kinematics equations to solve. Alright, so now I've got these two equations, and you pretty much have to have acceleration and time to be able to solve anything. Well, I can create a third equation from the two. So I'm just going to do some algebra here where we eliminate t. So then you don't have an equation that has t in it at all. So I have v is equal to v naught plus at, and delta x equals v naught t plus 1/2 at squared. I can solve for t in the first equation, v minus v naught over a, and substitute that back into the delta x equation for the t. So then v minus v naught over a goes into our delta x equation. Now I know that looks ugly, but some ninja algebra and it's going to look better. So delta x is equal to, let's, FOIL this thing out, v naught times v minus v naught squared over a plus a over 2, just kind of simplified the 1/2 a, times, alright, remember how to do this? First term squared plus the sum of the two terms, second term squared business. Okay, so that is that function, that expression on the right, FOILed out. Okay, I want to first reduce that a and a squared on the right side. Now, I don't want anything in the denominator. I want a nice linear equation that doesn't have any more fractions than it has to have in it. So, we can multiply by a on both sides, and we can multiply by 2 on both sides. So let's just multiply by 2a on the right side, and 2a on the left side. And there I've just combined the 2 and the a on that right term over there. And now my a, the acceleration, can cancel out of the denominator because it's been multiplied. Alright, so now what's that reduced to? Let's see. When I multiply by 2, so the 2 on the far right term can also be canceled out. So I've got 2 v naught v minus 2 v naught squared plus v squared minus 2v v naught plus v naught squared. And that doesn't look very pretty. But if you look carefully, do you see like a negative 2 v naught squared plus a v naught squared? And do you see a 2v v naught and a negative 2v v naught? I think when I add those together I get 0, so those guys go away. Isn't that nice? So I have 2a delta x, and then let's combine like terms. So minus v naught squared plus v squared. Now negative signs are really bad to have in equations because we tend to forget them. So let's add v naught squared to both sides, so then we don't have to remember like which v gets the negative sign. So you have v naught squared plus 2a delta x equals v squared, and usually you'll see it written as v squared equals v naught squared plus 2a delta x. And that is the third kinematics equation. And remember, it comes from combining the first two. And the first two come from a velocity time graph. The equation of the line and the equation for the area under the line. And that's all there is to it. Alright, so v is the final velocity, v naught is the initial velocity, a is acceleration, and delta x is change in position. And the SI units are meters per second squared, and meters. It's important to always use your SI units.